Hello, everyone. So thank you for the introduction. So I'm going to talk about in-field testing using in-system IS-EDT. So this is pretty new feature from Siemens, and we have utilized in our one of our SoC. So in-system is pretty common word. I think most of the seasoned people here would understand what it is. I'll just give a little bit of brief introduction what it is about and what is that we are doing differently. So in-field testing or in-system test is when the SoC has been deployed at the customer end in the system, in the application. So at that time, we don't have the luxury of access to all the IOs the way we have on ATE. So we have to run the patterns, whatever we want to run, we have to do it in the system, right? I mean, with a limited access to the IOs and all. So that's what in-system and in-field term, that's where it comes from. But now we have been using in-system for a while now. I mean, it's a very common thing. What is different here is, what we have been doing till now is in-system for JTAG and IJTAG related, BIST related stuff. But what we are doing here is, we are running deterministic patterns, that is EDT patterns, in the system. So that's what this is about, and I'll proceed. Okay, this is the agenda. So I'll just talk about a little bit about the motivation why we need it. What there can be multiple reasons or multiple application of it. I'll touch a couple of them, which is what made us do it. Then what is the Siemens IS-EDT solution and how we customized it for our implementation, our design specific stuff. Then I'll talk about some data, and then what are the design challenges we faced and the tool enhancements which we got done. Okay, and I'll stop in the middle just for one or two questions, and there's where I explain the architecture. That is one of the important slides, and then we'll have Q&A at the end. Okay, so I think everybody associated with DFT has heard this term. This is it was a pretty hot topic in last year's ITC as well. And this is something which we have taken from our customers' slides, that silent data corruption has caused interruptions in the system, and it is a real problem. Okay, so to tackle that, this IS-EDT comes in handy. So there were a couple of reasons, a couple of motivations here where we can address this problem. One is that one of our customers, they told us that, okay, for the AI applications, we want to allocate a time, let's say every few weeks or every few days, and we want to run all the tests or targeted tests, and we want to test whether the system is alive, it is working fine. So, but we don't want to add any extra BIST hardware, so whatever we have, like the EDT stuff and all, we want to reuse that as much as possible. And other thing is that with the changing technology and all, if we have some top-up runs, if we have top-up patterns or some new patterns, new fault models, we don't need to take out the device from the system and then ship it back to the lab and then run the test there. We can run the test in system as well with the new patterns or new fault stuff. Okay. So this is the Siemens IS-EDT solution. So as I said, right, in-system test for BIST and IJTAG, JTAG has been in place for a while. We have been using it for years. So the original one, or I would say the one which had IJTAG interface, now has been enhanced to use SSN interface as well. So one very important point to note here is that SSN, this new solution, this IS-EDT solution, works with SSN only. You cannot have the EDT driven directly or anything. You have to have SSH in place. Okay, so, but we did not have SSH. I mean, we did not have full SSN design. We did not have SSN in every block for the chip, particularly the chip for which we were trying to use this. Okay, so that's why we had to come up with our own solution. So we had to implement this IS-EDT specifically for the chip. I'm just talking about that. I mean, It can be used even for full SSN. That's what Siemens recommend. But specifically for the chip where we do not have the full SSN, where the SSN is sitting in every block, we still wanted to use it. So this is the block diagram. I will spend a little bit of time on this one. And I'll try to explain this. I don't have a laser to point, but I'll just try to explain this. So on the right-hand side is a targeted block for which I want to run the ATPG patterns. And before that is the EDT channel muxing, which is actually, it is just, there are a lot of in-test modes, right? We have multiple modes. So it is from IO to the EDT channels. That's what it would be. And all this orange logic, which you can see, that is the stuff which we have added just to support this feature. That is a new logic which we have added, you can say. And all the blue ones was existing without this feature in the design. Now, if I get back, then we had to put one SSH. So as I said, we did not have SSH in our blocks, so we did put one SSN only at chip top. That talks to my EDT channel muxing, and that talks to the targeted block. And we also put we use the IST with SSN interface, the enhanced one, the new one which supports IS-EDT. So there was no change done to the blocks, nothing at all. By the way, the right-hand side targeted block, that is like 90% of my chip. It may not be shown to scale, but it is like most of the blocks which exist in the system, except for some of them, which I will talk about, what are not included in this. Okay, so the way the data flow works here is, so there is an on-chip SRAM, and there's a CPU on the left-hand side of the diagram. If you see, there's a CPU and there's an on-chip SRAM that talks to IST controller through APB interface, and then there is a muxing, or it directly controls the SSH, which controls the EDT channel of the targeted blocks, and the data comes back in the same path. So the way the data flows is we load the data in the on-chip SRAM through some external interface. Now that external interface can be SPI for the least lowest speed, or PCI controller, or USB, whatever it is, based on your design. You can load the data, the pattern, the IS-EDT pattern, in the on-chip SRAM. The CPU goes and reads it from there, puts it on the APB interface of IST controller. From there, it controls the SSH, which in turn controls the EDT channel muxing, and it drives the data into the EDTs of the targeted block. And this one, the way we are targeting let's say in one in-test mode, one of the ATPG modes, we have, let's say, 3 blocks, 4 blocks. That grouping remains the same. So we are just reusing the patterns, what we would use on the ATE for the IST. So we are targeting the exact same patterns which we used on ATE for the in-system. So which is a good feature, because there is a one-to-one mapping between what we have, the results we have on ATE and what we get on IST. So the data flow is, again, going from CPU to ISTK to SSH to targeted block, and the data from EDT out coming back to SSH, and that loop path from the top, if you see, that coming back to the IST controller. And that is, again, read by a CPU through APB interface. So that's the data path which is shown here in orange color. From the area point of view, it's just a dot on the floor plan, really. And it is less than 200 flops. And if you include all the combos and all, it's around 5K. So it's very, very small. And the other logic for the SSH, which we had put for this particular purpose only, and all that data muxes and the IJTAG and all that programmability TDRs and all, it was less than 1,000 flops and 30K equivalent NAND gates in 5 nanometer. And by the way, this is for 32-bit APB bus and 32-bit SSN bus. So it can vary a little based on your configuration, but the point here is that the area is not a concern at all. Okay, so I think I'll be coming to your question on that memory usage, right? So because we are talking about deterministic patterns here, as opposed to, let's say, logic BIST or something, which is a BIST, and you just trigger it. Here we are talking about deterministic patterns, and the data, the volume is huge, right? And we are trying to utilize the on-chip SRAM. So there are some calculations which I'll show that how many times you have to load the memory to get some valuable coverage. So let's say we have 5 in-test modes, and we have 20. By the way, this is a real data from the chip where we implemented this. So we had 5 in-test modes, and we were trying to target 2,500 patterns in each mode. These are stuck-at patterns, and the on-chip SRAM size is 2 megabytes, which is around 500,000 32-bit words. So I would say this is a usable part for the SRAM, which we could use to execute the patterns. Okay, so this is the data from the sample patterns. So we generated the IS-EDT patterns for all the 5 in-test mode for the sample set of patterns. So around 35 patterns, we needed 260K of 32-bit words. Now, if I extrapolate it for 2,500 patterns, what we needed, so I need around 2 million 32-bit words to cover 2,500 patterns for each in-test mode. Now, that has to be multiplied by 5. So I need 4 loads for one in-test mode. Okay? And this is again with one SSN, which is sitting just at chip top. The blocks are still with EDT. If we have what we call a full SSN design where the SSH is implemented in every core RAD block, then the data is supposed to be, the numbers are supposed to be substantially better, because all the SSH advantages will be, we can fully use it. Okay. Okay, I'll talk about some design challenges. Obviously, I cannot list all of them here, but whatever I could, I'm just trying to touch those. And okay. So I think this terminology is clear from that architecture diagram I showed. The functional blocks are the ones which are used to execute the IS-EDT operation, and the targeted blocks are the one for which we are targeting the ATPG patterns, which are to be in scan mode. So some part of the chip will be in functional mode, which is executing from SRAM, CPU, which is reading from SRAM and writing on the APB interface of the ISTK. And most part of it rather, would be targeted. Okay, so on the right-hand side, I'm showing the functional block, which is CPU, let's say AXI to APB bridge, whatever, NOC, or the arbitrator, whatever it is, right? I mean, the one which is absolutely needed to put the data on the IST. And then on the left-hand side is a targeted block. And in between that, we have the isolation, okay? So this isolation, we need the CPU to operate in functional mode. Now the blocks for which ATPG patterns are targeted, they are toggling. And they are toggling randomly, really. So we cannot have the CPU getting disturbed. Let's say there is an interrupt coming from one of the targeted blocks. Now if that reaches CPU, the whole operation will go haywire. So we need to isolate it and keep the CPU, as I say, in the quiet state. So this isolation can be, I mean, if it's a reset, for example, active low reset, it can be an OR gate, AND gate, if we need to keep it low, or clock gating to gate the clocks which are coming from or through the targeted blocks. Now, other than that, we also need to isolate the test signal, because let's say scan enable. So I don't want my scan enable to toggle or to get asserted for the functional block. Now, if these are broadcasted global signals, then you have to have some gating to be implemented specifically for this. Now, it can be done at the output of the targeted block, at the input, or at the input of the functional block. That's an implementation detail. Okay. Okay. So the way our clocking methodology in Broadcom is, we have PLLs at chip top, and we try to put, or rather we put the OCCs at chip top. We don't have the OCCs at the block. I mean, there can be a lot of questions. I mean, how will we generate retargeted patterns and all? I'll not go into the details. This is you can just take it on the face value that yes, this is a requirement that we have PLLs and OCCs, or let's take it as a scenario when we have a PLL driving a targeted block as well as a functional block. So for normal EDT patterns, we'll have a common OCC, and which can drive both of them. But here the problem is when we are in IS-EDT mode, the functional block needs a free running clock, but the targeted blocks need the OCC to be active. Now this is a problem, right? So we came up, we thought of some couple of solutions. One is that, okay, you just create a divergent path, very layman way of doing it, but sure, we can do that. Implementation won't be happy about it because we are creating another clock path, right? So the other solution which we came up with, we won't have a mux, and we'll put another OCC here, right? And we will make the first OCC, the original OCC, transparent, and this one will be active. So that way we can solve this type of problem. Okay. Another problem which we faced was this STA, right? Now, generally, the way we do the STA, it's different for DFT modes, different modes for DFT and different modes for functional. Now, this is kind of a tricky mode where we have some blocks in functional, some blocks in scan. So we had to come up we came up with a merged mode, but we also had to come up with some innovative ways to actually cover it in the existing modes, most of the paths, and then we came up with a merged mode as well. It would need a complete separate presentation if we need to cover all the things which we did for STA, but I just wanted to mention here that it adds some complexity to STA as well. And another problem which we faced was that verification of this thing is to be done only in the DV environment. When I say DV is functional verification environment. So all the collaterals are provided by the tool. We have whatever we need, transaction files, C files, system verilog tasks, everything is there. But still, it is something that we are running scan patterns in the functional verification environment. So which generally we don't do, right? So there is a lot of handshake and a lot of debug which is needed. It is not an isolated DFT task. It involves DV or verification team as well, functional verification team as well. So it's not just the deliverables that we have to give. The way when we implemented it, so we had to work very closely with them to get this implemented. I want to mention that the Siemens tool does provide us the test benches to verify it in DFT, but that starts from the IST input. So IST controller input. So from the APB and down through the SSH to the targeted blocks, we can verify everything. But in the system whole system environment, like functional block, reading from SRAM, and then putting it on the APB, all that has to be done in a verification environment. So the real verification or the true verification is done in a functional environment. Okay, so there are some tool enhancements. I think most of them, or maybe all of them, have already been implemented now in the tool. We worked with Siemens on that, and we worked very closely. When we started working on this was a beta feature in the tool, and now it's a product and with a lot of features really. So we worked with them to get these few enhancements. Maybe I can mention a couple of them from here. So APB clock, right, which is coming from, which is an input to the IST controller, and SSN clock, which is an output. So we asked for a divider or some option to have a divided clock there. So that feature was implemented, and that is now part of 24.4 and later versions. And then for writing out the pattern also, because we have multiple loads, right? So we asked for a feature that if we can specify, okay, this is the memory size, and we will create multiple files based on the sizes, rather than, okay, minus max load 20 or 25 patterns that way. So yeah, these were a few things which we worked with them, then some debug messages and all, we asked for that. And I think, as per my understanding, all of these are already part of the product now. I think that's pretty much I have. Okay, I'll go to the summary. Okay, as I mentioned, there is increased usage of in-field testing. I mentioned a couple of points where we saw the benefit, but there can be more application for sure. We had done successful implementation, and we have verified it properly in the DV environment, in the DFT environment, and the latest result we have from silicon, we have one pattern, one sample pattern passing on the silicon as well, and we are working towards other patterns. When I say on silicon, it's on the EVB or the functional board. Okay, and we are still collaborating, continued collaboration with Siemens, and for the next gen thing, and even to enhance this thing.